kind of convince you that this unit is just like unit 7. It just looks differently, okay? I hope you saw the connection with the rate problems to the problems you had on your test, and a lot of you have your test back because you were absent last class, where you had an equation of v. You would graph v because it was a derivative. You would do a sign analysis of v. You would figure out the signs of v, which is a derivative, and that tells you if things are increasing or decreasing. And you would incorporate some position at some time, and you would find future position. I hope you saw that the rate problems were just like that, right? With one addition, you had two velocities going in. You had like a rate in and a rate out, but we ended up with, the same kind of deal. X of b equals x of a plus the integral from a to b of v. Well, now we had p of b equals p of a, or p of 0 plus an integral from 0 to b of p prime. Guys, day 2 is just like the questions you had on your test, where the graph of v was given and the areas were given. You guys love those problems, right? If I told you this was 1 and this was 2, and I told you x of 2 was 4, you guys tell me some other positions. You guys tell me a max. You guys tell me a min. Go. This is 1. This is 2. Oh, you guys are wrong. All right, let's see if my velocity, which is my derivative of my position, is positive until 1 and then negative until 2. And I know x of 2 is 4. And I know my position increases then decreases. And I know it increases by 5 then decreases by 2. Make sure you're right on what x of 1 and x of 0 is. Were you correct? That x of 1 was 6. Yes? Good. If we go backwards, we don't add this negative area. We end up subtracting it. We got to do the opposite to go from where we came from. That way 6 minus 2 is 4. We have to do the opposite to go back in time. The questions you are going to see are the very same ones as these. It's just going to look different. Okay? One key difference is that areas are not going to be given to you. You're going to have to find them. But you don't have a calculator, and you don't even have equations. You'll just have graphs. Now, you might think, hold on, Mr. Messer, let's go back to this one. It's like, okay, let's go back to this one. How do you find the area of this without a calculator? Let's switch this to 0 to 2. Hopefully you're thinking, Mr. Messer, I either type this into my calculator, but without a calculator, how would you have to find this area? Tell your neighbors, please be correct. Don't say the answer is 4. If you say the answer is 4, I'm upset. Hopefully you are saying, all right, hold on. Okay, so for this one, no calculator, I'd have to take an antiderivative. Mr. Newton told us, like, yo, to find an area, you have to take an antiderivative. What I'm telling you is that without a calculator, you will be able to find areas without taking antiderivatives in this lesson, because we are going to see straight lines. That is a straight line, okay? Now, we know integrals as being areas. We're also going to think of it as like an accumulation. Accumulation, like we are adding up, and when you see your calculator do this, your calculator adds up all the y's. Your calculator adds up all the y's. Tell Sewell to go away. Give her a bad stare. Later, Sewell. Okay. Guys, it's like, well, I can't take an antiderivative, Mr. Mester. What do I type into my calculator, Mr. Mester? Don't worry. It's a triangle. This is a triangle. You guys know the area formula for a triangle. Tell your neighbors. Okay. The big difference between stuff we've already done and today is like, yo, you're going to have to find some areas and you're going to have to use some geometry. 1/2 base times height. This area is 2. One thing that might get confusing, though you're cool with this, you guys remembered that when your velocity was negative, we said our displacement must be negative, or our area must be negative, right? When you see graph underneath the x-axis, we are going to say this area is negative. The base of 1 and a height of 1, but I'm going to say that height is -1. I'm going to say this area here is -1/2 because it's under the x-axis. And what we're going to find is that what we're given the graph of is the graph of a derivative, just like we are given the graph of velocity. We will look at signs of our derivative for when our original thing is increasing or decreasing. We'll look at the areas for how much it increases and how much it decreases. Adding the 2 and the -1/2, we'll get 1/2, okay? Now, sometimes you will encounter some quarter circles or semicircles. Just remember that the area of a circle is pi r squared. You might have to make it a quarter, make it a half. You'll practice that on your homework. We're not going to spend time on that because we're just dealing with triangles and rectangles for today's lesson. I want to keep it simple. Got it? Okay, cool. Now, we are comfortable saying that when we are above the x-axis, the area under a derivative is this positive value, this positive displacement. And when we're below the x-axis, it's a negative area. But that is only because we are starting at a value less than where we end. It turns out order matters. Go ahead and in your calculator, just really quickly, and then we'll put our calculators away, type in this integral and get 8/3. But then type it in again, but switch the numbers. What do you think is going to happen if you switch the numbers and all of a sudden you go from B to A? What if I go to the left? What do you think happens? It is the opposite of what we would expect if we went from left to right. This should intuitively make sense to you if you understood why we did not subtract 2 from 4, why we added 2 to get to 6. When we went from right to left, we did the opposite of what we did from left to right. Is that cool? Okay. So what we will see is sometimes you're going to have to understand, yo, I'm going from right to left. And this area up here, I'm going to still consider a positive value and a positive displacement, but my answer is going to be a negative value. And this, even though I'd consider this a negative displacement, I'd say my answer would be a positive value. Okay? So I'm just going to keep this. It's like, it's just going to be the opposite of what I know, and that's what I'm comfortable with. Here's one other thing that we have not yet encountered, though intuitively we should be able to figure it out. What if we start and end at the same time? What if we go from A to A? What do you think it is? If you said 0, great, and you can check that. using your calculator, but intuitively it should make sense. What have we usually found areas under? Derivatives, like velocity. What have these usually been? Time. From the first second to the third second, 1 to 3, area under velocity from 1 to 3. Well, there's no time elapsing if I'm going from A to A. There's no time to move. There's going to be no displacement. There's going to be no area. It's not going to be A. It's not going to be the Y value. It's literally going to be 0. Okay, cool. Here we go. This lesson is on the accumulation function. The accumulation function is that guy. It is some integral from some starting point. This could be any number. It does not have to be 2, but the number is important for something. To a variable of some function. It's saying accumulate f from A to f. Add up all the f's like your calculator does when it finds the area. Add up all of those y's from here to here. Accumulate f from A to your unknown. And usually you will not see this accumulation function by itself. It will be equal to something else. Now here's the first thing people worry about. What the heck is going on with like x's and t's? Well, first things first, you can almost ignore the t and the dt. And it's just like easier. This function g equals the accumulation of f. Oh, here is the graph of f. That's f. The accumulation of f from 2 to x is g. Okay? Now, before we go and investigate g and find some values, we are going to do the most important part of this lesson a little bit earlier on, which is take the derivative of this. I'm going to be skipping around a lot, and I'm sorry, next year's students are better off than you guys, but you guys are better off than previous students that I've taught, okay? Cool? What do we think the derivative of this is? What do you think this derivative is? Well, here's where we're going to be a little bit confused, because you're going to say, oh, that's not even phone, wow. You're going to be like, yo, Mr. Messner, I'm not sure. I know that if I take the derivative of an integral, that an integral means take the antiderivative, and if I do this, I'm just going to get f. But now that I have this guy here and that guy here, I'm not sure what to do. But what I'm about to tell you is that the derivative of this is f. And that this doesn't matter. Why? Well, let me walk you through it. Go down here on the next page. Let's turn this into regular f. This is the more formulaic way, and then I'm going to go back to like that first page, and we're going to find some values, and then you're going to see, oh yeah, this makes sense in a less like formulaic or notational way, okay? If I were to evaluate this and I didn't have a calculator, now this is not what we're going to be doing, this is just me showing you that this pi over 6 doesn't matter, and that like f just gets replaced. Like when you take a derivative of this integral, that this stuff doesn't matter, you're just going to get f. I'm going to take the antiderivative of f. And I say the antiderivative of f is big F. And I'm going to say, okay, that's big F plus C. I don't really care about the C, but I'm going to plug in pi over 6, and I'm going to plug in X. And I get big F of X minus big F of pi over 6. Cool? I just kind of rewrote this by taking an antiderivative, by doing a change in a position, change in an antiderivative. Well, if I took the derivative of this, it'll equal the derivative of this, right? Okay. The derivative of big F is regular F. The derivative of big F of pi over 6 is 0. Because big F of pi over 6 is just a value. You might not make, this might not make sense to you right now, but I'm going to show you another way to do it. But this is how I'm going to try to prove to you one way that if you take a derivative of an integral, this doesn't matter, this doesn't matter, it'll just go away, you'll just get F. Go back to this previous example, okay? Well, let's first find some values of G. Let's just start at the start without worrying about a derivative. We are told G is the accumulation of F from 2 to X. If I ask you to find G of 4, 4 is replacing X, you will accumulate F from 2 to 4. Does everybody follow so far? Okay, since we have straight lines, we can think of kind of what my calculator does, which is like add up all of these F's, accumulate these F's, but we realize we have a rectangle or actually a square worth of area. It's a base 2, height 2. I'm going to get the answer 4. I would like you to find G of 7 and G of 2 and G of 0. And while we're at it, find G of 5. Go. Do a little bit of work. All this is just some geometry and areas, and you guys are filling in like the areas under this function. You're already good. Great. You've got the answers if you need them. It really is. This is easy, but like, I love it. He's like, it's like 8th grade math. Like, really not, but I love it. Come on, write down the numbers. Don't just wait. Now, guys, you have to pay attention to this 2. This is where your integral starts, okay? This 2 is very important. This is where I'm starting. Pay attention to that 2. All you're replacing is X with your number 4 or X with your number 7. X with your number 5. Come on, you have to do it. If you don't do it, then you won't see the beautiful thing. Okay. Ready? We got to move. Let's go to g of 5 next. It'd be 2 to 5 accumulating f. From 2 to 5 accumulating f, I'm going to get 5. Good? Now, if I were to go to 7, from 2 to 7, I would have to add that -2 and I get 3. Are we good with that? If I do g of 2, this is the interesting value because we have an integral from 2 to 2. That's 0. If I go and ask you about g of 0, you should be thinking, oh, it's the opposite of 0 to 2. 0 to 2 would be +3. This must be -3. Now, ready? I'm going to make the connection with what we've done before. Yo, all this 2 provides is like a starting point. All that this value provides is a value you know. It's like when I gave you the position at time 2 is 4 in the previous problem. If I gave you the position at time, over here, the position at time 2 is 4, that was your starting point that you had to use. You are getting a starting point with this 2. Now, what you're told is the position at time 2. I don't know how we went full screen, but I love it. The position at time 2 is 0. Okay. When you take your derivative of g, I'm telling you that this won't matter because it's just an initial value. And when you take a derivative of initial value, it goes away. And g prime is just going to be equal to f. What we will figure out is that this f graph is actually the graph of a derivative. It's the graph of a velocity. It's the graph of v, and you just found the area. Well, what do we do with graphs of velocities, with graphs of derivatives? We look at their signs. Okay, let's do a little bit of analysis, and I'm going to split this up for fun. It's positive until 2. Yes, it is positive at 2, but I'm going to just say it's positive until 2. It's still positive until 4. Yeah, it's still positive 4. But really the key point is that 5 is where the signs change. And then it's negative. Cool? What did you guys find? G must increase, 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 and then decrease. What did you find? G of 2 was 0. That is something you'll always know because that's your starting point. If you go from 2 to 2, you got 0. Now look at your areas a little bit differently. Oh, from 2 to 4, I had an area of 4. Oh, add 4, I get G of 4. From 4 to 5, I have an area of 1. Oh, G of 5 is 5. From 5 to 7, my area was -2. Oh, this is the areas under G. These are the displacements. This is the area under G prime. This is the area under F. But the area under F is an area under a derivative because F is the same as G's derivative. You see how it all works out. And you even see the beautiful idea of going backwards. G of 0. Well, my area here was +3. Well, you have to add 3 to get to 0. You must come from -3. Cool? So, even though it looks funny, you're going to have this funny looking accumulation function. It looks weird. Turns out the inside is just the derivative. You're going to start with this function equal to this funny looking function, but it's going to be easy because when you take the derivative of both of them, you realize this graph that's given to you is just a derivative. Okay? Now I'm going to skip a bunch but you're going to be okay. We're going to practice this. Skip. Yeah, find this guy. And do me a favor. Connect them with straight lines. And answer the following question. What is G of 1? What is G prime of 2? We will talk about what G double prime is in a second, but maybe you can figure this out. Then I want to have you answer, when does G have a absolute max and what is its value? This is like the questions, when are we furthest right, furthest left, max, amount, and then we'll talk about points of inflection after that, okay? Don't worry about G double prime yet. We'll talk about that in a second. I just want you to find G of 1, G prime of 2, and then tell me where and what are the values of the maxes and mins of G. And you know what? I'm changing my mind. I'm sorry. I'm already apologizing. Change this to 3. Different starting point. I'll also help you out really quickly. I'm going to tell you what the areas are. From 0 to 1, this is a rectangle, base 1, height 4. This is an area 2. I'm going to split this into little pieces. This is going to be a -2. This is also going to be a -2, which means this is all together a -4. This is a base 2, height -2, so this is also -2. Rob, we're not using our calculator here. All right, go. We're starting at 3. Find G of 1, find G prime of 2. Do the sign analysis of G prime. Do your full-fledged sign analysis. Find the absolute max and min values of G. What I tried to convince you is that this number 3 doesn't matter. The fact that we have x here doesn't matter. The t, zt doesn't matter. The 3 gives you a starting point, but the derivative of G is actually f. F is a rate. It's like on your last sets of problems when you were given a rate is h. Your rate in is this h. F is a derivative. F is G prime. Go. Come on. We got to try. We need to talk. We need to see if we know this. Well, yeah, what are the max mins? You got it? Well, if this was bigger than that, then that can't be the min, and that can't be the max. It's an x value. You can think of it as a time if you want to. Find the max and min values of G. Max min values of G. That's the most important. We'll go back to G double prime. Don't worry about G double prime. Do the absolute max min value analysis. Tell me the maximum level. Tell me, when am I furthest right? Go. Come on, do it. Okay, good. I like that. Just keep going. If you haven't done a sign analysis yet, please get a sign analysis down. For the love of everything. The sign analysis is so important. What's the maximum over here, guys? Your value's wrong. They are? Yeah. I didn't think you found the areas correctly. This is -2. And I'm starting at 3, not at 2. All right, then. You guys get over there, Hedrick? Let me see. What's the min? You got the max. What's the max and the min? Did you guys get it? That's right. Pay attention to Hedrick. She knows what she's doing. Good. No, that's good. It's a good start. All right, guys. I wanted this to be like, oh yeah, I got this. It doesn't seem like it is. I'm going to show you it's something you've already done. It just looks a little different. If you can get over like the crazy hump of the derivative of this whole right side is just f, then you know that this is the derivative of g. Let's do a g prime, which happens to be f sign analysis. It's positive until 1. It's negative after 1. Okay? Now, we could split that off into, like, different kind of sections because we did have this starting value of 3. And that is a 0 of the derivative, so that's okay to do. Now, guys, this is a very, very important value, this 3, because you know g of 3 is 0. If you go and plug in 3 in for x, your integral from 3 to 3 is 0. Super important. Now, if you have that starting point, you know the areas and the displacements. You know the areas under F will be the displacements of G. The areas under G prime. How much G is changing? I asked you what G of 1 is. Sure, you can go integral from 3 to 1. This is probably what you need to show. But look at what you have. You have G of 3 is 0. You subtract 4 to get there. Oh, yeah, it's going to be the opposite from 1 to 3 as it is from 3 to 1. So I must have come from positive 4. That's got to be my max. Why does it have to be my max? Because G prime is positive until 1 and negative after 1. What's my min? Well, if I have 0, I'm going to decrease 2 to get G of 5 is negative 2. If I have 4 and I increase 2, I must have come from positive 2, and that's G of 0. These are all of my values that I need to pay attention to. These are my candidates. When my derivative is 0 or an endpoint. All this provided was a starting point. We use our areas to fill in the rest. This is something that we are familiar with. The min is G of 5, which is negative 2. What is G prime of 2? Now, here's where some questions are going to come back to us from way back in Unit 3. And where they come from should be like, oh yeah, I remember this stuff. Oh, concavity is going to show back up. Second derivative sign. We are going to see a first derivative sign analysis, which will be F sign analysis. We're going to be given the graph of F. That'll tell me if G is going up or going down. But guess who's back? Back again, G double prime sign analysis is back, which tells me if G prime is increasing or decreasing, it's telling me if G is concave up or concave down. He's back. Okay? So, going back to this question, I'm going to ask you, what is G prime of 2 and G double prime of 1? I've already done all of the good sign analysis. Let's just forget about this. It's all beautiful. But now tell me G prime of 2, G double prime of 1, and then when does G have a point of inflection? All great questions that we haven't seen in a while, but they never went away. Sorry if this is busy. It'll be better in future years. G prime of 2 is F of 2. Oh yeah, because G prime is equal to F. What's F of 2? This value right here. The y coordinate is -4. If I ask you for G double prime of 1, hopefully you're like, oh, well, G double prime is the same as F prime. G double prime, which equals F prime. What is F prime of 1? I want a very specific value. Tell your friends what that value is. If this is a straight line. Oh man, I don't like this. It's like the same. I hate repeated values, so this is bad. We'll go do another problem and it'll be fun. So, you're talking about the slope of F at 1. The slope of F at x equals 1 is down 4 over 1, -4. So that's the y value, but that's the slope. Where do we have points of inflection? Well, we're going to bring back our friend, Mr. Second derivative sign analysis. Or first derivative direction analysis. F goes down until 2. F goes up until 3. Wait. Yeah, 2, 3, 4. It goes down until 4. Not 4, 5, 6. 2, 3, 4. Is that what you said? Okay. The slopes of F are negative, then positive, then negative, and then it's positive from 4 to 5. 1, 2, 3, 4, 5. Yeah. Which means G's concavity, which so happens to be the big F, the antiderivative of F, but don't worry about that, is concave down, concave up, concave down, concave up. X equals 2 and 3 and 4. The direction of G prime changes, the direction of F changes, G will have points of inflection. Okay, let's go back to this guy. Now I'm going to change my mind. I'm going to say we start at 5. I'm going to ask you what is the absolute max min values of G. I'm also going to ask you when is G concave up. This is like below that previous question. Don't worry about accurately sketching. Just tell me what is the absolute max min values of G. Tell me when is G concave up. And then give me a couple values. What is G prime of 1? And what is G double prime of 1? Go. 3 parts to this question. Go. We got to get this right, and then I'm going to throw a curveball at you over the last 10 minutes. You got 3 minutes to get this right. You got it. Come on, come on, come on, come on. I always start with a sign analysis, Rick. Always where I like to start. A sign analysis of a derivative is always a good place to start. Not sure where to start? Throw down a number line and see if you can do a sign analysis of the derivative. Now, another good place to start is to understand that the derivative of G is F. That's a good place to start. Another good place to start is paying attention to that number. That's going to help you. That gives us our initial point. It's not going to affect the derivative. Everything's going to be fine. Zero? No.
I don't even know how to do it.
And we change that to 5. You got a second derivative sign analysis down. I love it. Got a lot of stuff. Got a lot of stuff. Got a lot of stuff down. Now, how do we fill it in? The slope would be 0 if it's flat. I'm just asking when is G concave up. But yes, you're right. If I were to do a second derivative sign analysis, I would say like there's an interval of inflection. All right, here we go. Let's see if you're at least mentally on the right track. Okay, what do I have? I have the graph of G prime. That's the graph of my derivative. What did I find? A bunch of areas under the derivative myself. I had to do that. That's the only difference between this and the velocity graph questions we had last unit. I am seeing that the signs are positive then negative, which means G's got to be increasing then decreasing. I know that actually G of 5 has to be the max, and the max value is 0. This wins because G prime is positive until 5, and then G prime is negative. That means the min must either occur at 0 or at 7. Well, I know that this area from 5 to 7 under G prime, this area under F is -2. I know that G of 7 has to be -2. That is a min candidate. However, 3 plus 4 plus 1 is a positive 8, which means I'm increasing 8 to get to G of 5 equals 0, which means if I go back in time, I know G of 0 is -8. When you change your starting points, you don't really change the locations of your maxes and your mins. You just change their values. You change where your 0 is located. So boom, there's my max. There's my min. Winner, winner. When does the max min of G? When G prime equals 0 or an endpoint. Cool. What's G prime of 1? I'm going to do that first. That's F of 1. What is F of 1? That y coordinate. That y coordinate happens to be 1.5. You can find that by applying a slope and figuring that out. What's G double prime of 1? Well, that's F prime of 1. I'm looking at the slope of F at 1. That's going to be up 1 over 2. So I got 1.5 and I have a half. Cool. When is G concave up? Let's look at this last question. And then I'm going to really throw a curveball at you. G is concave up when G prime is going up, or when G prime slopes are positive. G double prime is equal to F prime, G prime is equal to F. You want to know when G is concave up? It's when F is going up. Where is the graph going up? From 0 to 2. How do we do? Hopefully you're seeing, oh, this is stuff we've already done. You just got to maybe like practice, freshen up on it. Okay, now I'm going to blow your mind. Everything's going to change, and you are going to hate me. All right. I have the same graph, same exact graph. We're on the next page, okay? But I'm going to change the questions. I'm going to ask, what is G of 2? What is G prime of 2? And what is G double prime of 2? I'm then going to ask, when does G have a max? And what is its value? You know what, let's start with the easy question. Everybody pause. Let's start with the easy question. And again, I'm telling you right now, this is your curveball. It's going to be a curveball right now, but once we get to the next class, it's no longer a curveball. You're ready for it. When does G have a max? What is its value? All right? Answer that question. What's the max value? What is the max? Go. Here's what happens, guys. Here's what happens every year. Every year. Students think all problems are set up the same, so they do the same thing for every single problem. Students see a graph of f, they see an integral, they assume, okay, we're good. All I need to do is my sign analysis, and students are like, okay, 5 is my 0. We are positive until 5, we are negative after 5. So my max must be at G of 5. And you are entirely wrong. Entirely wrong because of the curveball. There is something else besides just an integral on the right side. This is a different question that should be handled a little bit differently, but mostly the same. And how we're going to handle this is to realize through finding these values, oh yeah, things are a little bit different here. For example, if I found g of 2, we would assume, that since that's a starting point of 2, that this would be 0. However, if I replace x with 2, I realize it's 2 plus the integral from 2 to 2 of f. And g of 2 is actually the value 2, not the value 0, because this curveball. Then, if I look at the derivative, we think the derivative of g is just f. So a lot of people will type down 2 because they're like, oh, that's the point on f. You are wrong. Because what do you get when you take the derivative of this right side? Paul Rock, I heard you, and you're right on top of it. 1 is the derivative of x plus f, which means g prime of 2 is not just the value of f at 2, it's 1 plus the value of f of 2, which means my answer is 3. Which means this derivative of g has to be analyzed as 1 plus f. Now, what's nice and what saves a lot of students is that when you take the derivative of 1, it's just going to be 0. So you just get f prime and g double prime of 2. It's actually undefined because there's a sharp point, but whatever. Let's get to the real question of where do we have a max? Okay? Let's analyze the signs of g prime. Well, you're not going to pay attention to this. You're not going to pay attention to that x equals 5. The graph of f is not what we want. We want the graph of 1 plus f. How does that look? What would you do if you want the graph of 1 plus f? You shift everything up 1. And guys, this is your graph. That's a curveball. Yo, 6. Now, here's another thing you could have done. When do we have a max? A max, g, is when g prime equals 0. Oh, that's when f's going to equal -1. Does that make sense that f has to equal -1? The other way to get this location of 6 is to not pay attention to the x-axis. Rather, pay attention to the y equals -1 axis, and boom. Now, from here, we do get the direction of g. We do know the max is going to be at g. But watch how it gets tricky. If you want to find g of 6, it's really confusing when you look at this shifted graph and its displacement, and you don't even know a 0. So you know what you do? You just go back to the original graph. You don't worry about displacement. You instead plug in 6 here and plug in 6 here, and your answer is 6 plus 4 plus 1 minus a half, which is 10.5. And that's the curveball that you need to be prepared for. But everything else should be the same as what you're used to.